In 1996, biologists Barry Sinervo and Curtis Lively observed a peculiar population pattern in the common side-blotched lizard. The males of this species are divided into 3 distinct behavioral types, identifiable by their throat coloration. Orange-throated males aggressively defend large territories containing multiple females. Blue-throated males are less aggressive and defend much smaller territories. Yellow-throated males do not defend territory at all. Instead, their coloration mimics females, allowing them to sneak into established territories to mate. Initially, the orange-throated males reproduce rapidly because their large territories secure more mates. But policing a wide area leaves them vulnerable to the yellow-throated sneakers, causing a yellow population spike. As yellow grows, they're driven out by the tightly guarded blue males. Once blue dominates, their smaller territories are overrun by orange males, and the cycle restarts. The lizards are executing a biological version of rock, paper, scissors. Orange crushes blue, blue blocks yellow, and yellow sneaks past orange. No single strategy can hold the top spot indefinitely. When humans play a game of strategy, they anticipate their opponent's moves. They evaluate the rules, form a plan, and make a conscious choice. The side-blotched lizard does none of this. It does not choose its throat color or its reproductive behavior, yet the interaction of these behaviors creates a highly complex problem of strategic choice. The optimal trait depends entirely on the current distribution of competitors. Nature poses and then solves this optimization problem through frequency-dependent fitness, without requiring a rational decision-maker. To map how these unconscious interactions reach equilibrium, we have to look past the rational actors of traditional economics. We have to examine the mathematics of evolutionary game theory. Decision-making falls into 2 categories. In parametric choice, you optimize against a static environment, like a farmer timing a crop harvest around the weather. But in strategic choice, your optimal move depends on the choices of others, who are simultaneously adapting to you. The traditional solution for strategic interaction is the Nash equilibrium, formalized by John Nash in 1950. A Nash equilibrium occurs when every player has settled on a strategy such that no single player has an incentive to deviate, provided everyone else keeps their strategy unchanged. Look at this 2x2 payoff matrix. When we apply the Nash concept to biological populations, a critical weakness appears. Consider a simple scenario representing evolutionary drift, where an entire population currently plays an equilibrium strategy called S2. Suppose a single mutant playing strategy S1 enters the population. When S1 interacts with the S2 majority, the mutant receives a payoff of 1. That payoff of 1 is exactly what the S2 individuals receive when they interact with each other. Because the mutant suffers no fitness penalty compared to the incumbent population, there is no selection pressure against it. It can persist and it can multiply. As the S1 population grows, they eventually interact with their own kind. An S1 interacting with another S1 receives a payoff of 2. Now the S1 individuals have a definitive reproductive advantage, and they rapidly outcompete the original S2 population. The Nash equilibrium requires only that a deviating strategy does no better than the incumbent strategy. In this case, the S1 mutant did equally well against the incumbent, allowing it to gain a foothold. Because a standard Nash equilibrium permits exact ties in payoffs, it fails to block mutants from drifting into the population and eventually overriding the system. A stable biological model requires a stricter mathematical threshold. To locate that threshold, mathematical biologists use models like this hawk-dove matrix. This represents territorial conflict over a resource with a value v. If 2 hawks fight, they risk a serious penalty, incurring a cost c. The model is useful when the cost of losing the fight is strictly greater than the total value of the resource itself. In 1973, biologists defined an evolutionarily stable strategy, or ESS. An incumbent strategy must first meet the basic Nash requirement. Its payoff against itself must be greater than or equal to an invading mutant's payoff against the incumbent. But if those payoffs are exactly equal, if the mutant matches the incumbent's initial performance, a strict second condition triggers. The incumbent's payoff against the mutant must be strictly greater than the mutant's payoff against itself. This imposes a second-order best reply constraint. If a mutant infiltrates the population and starts interacting with its own kind, The original population must be highly efficient at exploiting the mutant to drive its numbers back down. If a mixed strategy in the hawk-dove game achieves this ESS status, it means the incumbent strategy is a better response to every possible mutant than the mutant is to itself. The invading variant is mathematically suppressed. This is exactly what was missing in the evolutionary drift scenario. The incumbent S2 strategy could match the mutant initially, but it completely failed to outcompete the mutant once the mutant started interacting with its own kind. Meeting both ESS conditions creates a uniform invasion barrier. As long as the number of invading mutants stays below a specific frequency threshold, the incumbent strategy maintains a higher expected fitness, starving out the invasion and locking the population into a stable endpoint. Yet, identifying an evolutionarily stable strategy leaves a significant gap in the analysis. An ESS is a static concept. It confirms whether a specific mathematical condition holds at a specific moment in time. It proves an endpoint is stable, but it reveals nothing about how a population actually arrives at that endpoint if they start from somewhere else. Real biological selection is a continuous process. To capture the full picture, we must treat an evolving population as a dynamical system. The current state of the evolutionary system can be plotted as a single point in this multidimensional state space. This vector specifies the exact proportion of the population following each available strategy at any given moment. Within this space, the value of a strategy is never static. Expected fitness recalculates constantly. As the population ratio shifts, the probability of interacting with a specific behavior changes, immediately altering the reproductive payoff for everyone involved. To predict where the population goes next, we need a mathematical law to govern this state space. We need a system of differential equations that links current population frequencies directly to biological selection. This differential equation is the replicator dynamics, the engine of evolutionary game theory. The term on the left represents the rate of change over time for the proportion of the population following a specific strategy. On the right side, the first variable is the current frequency of that strategy. If the strategy is extinct, this value is 0, and the rate of change is 0. Inside the brackets, we have the expected fitness of the strategy. This is a real-time calculation of the reproductive payoff an individual can expect, given the precise mix of competitors. Finally, that expected fitness is compared against the average fitness of the entire population. This serves as the baseline for natural selection. The core logic of this equation is direct. If a strategy's expected fitness is higher than the population average, the value inside the brackets is positive, and the frequency of that strategy grows. If its fitness is below average, the value becomes negative, and the strategy shrinks. By running this system of differential equations simultaneously for every trait present, we can map the exact path a population will trace through state space, accounting for infinite combinations of mixed strategies over time. Applying this mathematical engine directly to the mating behaviors of the side-blotched lizard returns us to where we started. Because there are 3 strategies, orange, blue, and yellow, we can map the entire state space as this geometric simplex. As we start the replicator dynamic simulation, we track the frequencies of the 3 male types interacting across generations. The expected fitness of the aggressive orange males rises, pushing their population frequency upward. But the changing ratio recalculates the average fitness, suddenly granting an advantage to the yellow sneakers. Yellow overtakes orange. That frequency shift mathematically triggers a fitness spike for the blue defenders, who overtake yellow, which eventually clears the path for orange to rise again. The resulting phase space trajectory is a continuous outward spiral. The mathematics output the exact biological cycle observed in the wild. The introduction of evolutionary game theory resolved a critical bottleneck in understanding complex systems. We no longer have to assume that participants possess any awareness of the rules. There is no intention required, no forward planning, and no rational calculation. By substituting abstract human utility with the concrete reality of reproductive fitness, we secure an engine capable of precisely how unconscious strategies emerge, compete, and stabilize across the natural world.